Here's a challenge. Can we get a computer to generate Shakespearean text? Let's have a go. Here's a first attempt. Us, the insight o'er a land dam, are peace incarnate. Not very impressive. I generated it using exactly the same style of probability model that we've been using throughout this course. I designed a random variable distribution for generating values, in this case words, and then I generated a random sample, in other words a list of independent values x1 up to xn drawn from that distribution. This is called a bag of words model. And of course I don't need to do any work to fit the probability model, since the best fitting random variable is the empirical distribution. In other words, I just pick words at random from the entire text. Anyway, it's not very Shakespearean. Can we do better? The basic problem with picking words independently is that words shouldn't be independent. If you know one word, you can make a guess at what comes next. If I say wherefore, you're primed to expect art thou Romeo? This suggests we try a Markov model. Let's generate the next word based on the preceding word. We'll look up all the places in the text that the preceding word appears. We'll look at all the possible words that come next and pick one at random. To foreign princes lie in your blessing. God, who shall have the Prince of Rome? It's a little bit better than the bag of words, but still not great. Although I've been told that a really great actor can read a telephone directory and make it sound Shakespearean. Anyway, what could we do to be able to generate more convincing text? To explain the next approach, it'll be useful to have some notation. The Markov model, we generated words x1, x2, one after the other, generating each word based on the preceding one. In the bag of words model, there was no relationship at all between them. But what if we took the Markov idea one step further and generated the next word based on the two preceding words? Concretely, let's say we're trying to decide what comes next after some two-word phrase, for example, to be. We'd scan through the entire corpus, look for all instances of to be, and see which word comes next, and we'd pick one of those options at random. This is called a trigram model, since it's based on looking at triplets of words. It does make a bit more sense. To be windshaken, we will be glad to receive at once. This trigram model, though, it's a bit of a pain because it's not a Markov chain. Markov chains are handy to work with because it's nice and easy to write out the likelihood function, which is the basis for pretty much everything in machine learning. Here, the diagram's a mess. But there is a nifty trick which lets us see it as a Markov chain. Let's define yn to be the pair xn, xn plus 1. The neat thing about this is that yn plus 1 ends up being generated based purely on yn. The first component, xn plus 1, we just read off from yn. The second component, xn plus 2, that's generated based on the preceding two words, i.e. based on yn. And once we've got the y sequence, it's easy to extract the x sequence that we wanted in the first place. The point of this is that the y sequence is a Markov chain, since each item in the y sequence is generated based purely on the preceding item. And this is great for calculation because Markov chains are nice and easy to work with. Another way to put it, if we decide that it's worth using history, we can internalize that history into the state space of our Markov chain. This is actually the big point I want you to take away from this video. When you're modeling a dataset using a Markov chain, you should feel free to throw into the state absolutely everything that's relevant for generating the next state. The state space isn't something that's specified for you, it's something you invent based on what variables you think it will be useful to track. I just want to finish off by saying a little bit about current developments in sequence models. So far, we've seen the Markov model and we've seen the trigram model. The trigram model seems to generate better looking text, which suggests that it is useful to take some more history into account when generating the next word. And this construction we've just seen shows us how to internalize that history into the state space. This prompts the obvious question, wouldn't we do better if we used more history? What if instead of trigrams we used n-grams for some large value of n? There is a downside though to making n too large. If we made it bigger, say n equals 20, then any given sequence of 19 words is likely not going to appear more than once in all of Shakespeare, so there'll only be one choice for the 20th word. So if n is too large, all we end up doing is regurgitating the original text. Finding good ways around this history problem, keeping enough history to make a good guess about the next word, but not so much history that we slavishly repeat. This is an area of active research in natural language processing. In the 1990s, hidden Markov models became popular. The idea of these is that there's an underlying hidden Markov chain Z which can flexibly encode all of the history that's relevant, and each word xi in the sequence is just generated based on the current history state zi. The trouble with hidden Markov models is that they're a real nightmare to train because there's just too much flexibility in what the hidden state can be, and there's no clean, simple expression for the likelihood of a sequence. In the last decade, two types of neural networks have become popular for text generation: recurrent neural networks and transformers. Recurrent neural networks are an extension of the n-gram model in which we train a neural network to learn the most useful amount of history to keep, rather than hard-coding it to use exactly n words of history. They're still plain simple Markov chains, they just have neural networks to specify the transition probabilities. Here's some text generated by trigrams, by 5-grams, and by recurrent neural networks. In fact, these are all examples of generating text at the character-by-character level rather than the word-by-word level that we looked at before. The recurrent neural network is remarkably good. As for hidden Markov models, I think they've fallen by the wayside for text generation, although they still are in widespread use for other applications, particularly tracking applications. Here's an illustration. Let's imagine a stoat scampering about, and this red line shows its path, which in this simulation is a simple random walk. Let's say Zn is the stoat's location on day n. And now let's imagine that we have some other sensor, for example a low-res camera, that tells us some indirect noisy readout of our stoat's location. Let xn be the camera readout on day n. An interesting question here is, if we're told the x's but not the z's, how well could we infer the stoat's location? For example, if we see a string of whitish colours followed by bluish, we know it must be somewhere where there's mountain near to water. In the printed notes, there's a link to an Uber engineer describing how Uber uses hidden Markov models to denoise GPS readings. For them, Zn is the car's true location on the street map, and Xn is the noisy GPS reading, and they want to figure out what the true location is. They know enough about the street map and about how cars move to be able to come up with a pretty good Markov model for Z. In the example sheet, you'll be asked to develop a Bayesian solution to this problem. And the supplementary example sheet will ask you to develop the computational Bayesian solution called a particle filter, which is in widespread use in robotics. Let me just finish by saying a little bit about the history of Markov chains. This is Andrei Markov, a Russian mathematician. He invented Markov chains in the early 1900s. He was interested in the idea of using a Markov chain to fingerprint an author based on the typical patterns of how they used vowels and consonants. He realized that a simple Markov chain wasn't a very useful fingerprint, and he proposed the trigram model that we've been thinking about. And then he tabulated all the trigrams of vowels and consonants in Pushkin's poem Evgeny Onegin. It would be so interesting to see Markov's reaction to recurrent neural networks, which are just a small extension of his trigram idea.